Okay, so number 39 is this scary looking problem where they've given you here a limit expression. Limit as n approaches infinity of 1 over n times this sum going on inside right here. And they're trying to get you to express that as one of these integrals. This is a problem we kind of dabbled with just a little bit at the very beginning of chapter 5. And really we kind of went in the opposite direction where we were trying to come up for area underneath a curve with an expression that looked like this, and then eventually change that right here into a summation. So the way to approach a problem like 39, these are tough and I'm not sure you're likely to see many of them. It wouldn't be a terrible idea to try to think about each of the four options right here in turn and maybe kind of map it out and see what it would look like and see if you can get this expression to work out. But I thought we'd be a little bit more direct in trying to go through that one here. So here's what I tried to do on this one. It's going to take a little while to explain, but hopefully it'll make some sense. Okay, so this is the limit expression that we were given right here. And probably the important thing to understand here is that what we have going on inside the brackets right here, the only thing that changes is this numerator right here within that fraction within the denominator. And obviously here we're starting at 1, we're going to 2, and we're going up until we get to an n for that numerator, which means that we're going to have n terms added together inside those brackets. Now, if you remember what we were doing in chapter 5, we were trying to come up with the area underneath a curve here, any old curve that looked whatever it did, by taking your overall region here from A to B, and then by cutting it up into subintervals and making rectangles out of that. And the number of subintervals right here was always determined by n. So n is going to tell us the number of rectangles that we are dealing with here within this particular problem. And obviously, it's a limit as n is approaching infinity, but it's usually more helpful to think about n in terms of a finite number at the beginning of a problem like this. All right, so if n is our number of rectangles, we might be able to infer a couple of things from that. 1 over n then became the width of each one of those rectangles that we were dealing with. That 1 over n right there out in front was very often the width of every one of those rectangles when they were split up regularly. Now, if you remember, the width of each rectangle, we used to have a formula for that delta x was equal to b minus a all over n. That is exactly what's happening right here, and the n in the denominator in both cases is the same. That tells us that the b minus a here, the width of the overall interval that we're measuring the area underneath, is going to be equal to 1. I have that written down here in just a second. Oh, right there. So then 1 was the width of the entire interval, and there's the b minus a. Now that told you, as you were looking at your choices right there, that in the integral, starting at an a and ending at a b, those two numbers had to have a difference of 1. I was hoping to use that to rule out some choices, but unfortunately, all four of the options that we were given here have an overall width of 1. So no help right there, but still good to know. This thing is either going from 0 to 1 or from 1 to 2. Okay, what else do we think we know here? Now this gets kind of interesting. So if we take a look at what's happening right here, that first term inside your brackets that you're adding everything together right here is always going to be the height of your first rectangle. And this last term at the very end right here is going to be the height of the last rectangle. So let's go one at a time right here. If our first rectangle has a height of 1 over 1 plus 1 over n, and we know here that n is approaching infinity, we know that the bigger n gets, the more that this term right here starts to approach 0. So as n approaches infinity, this term just drops out and we end up with a 1 over 1 here. That makes it look to me then, everybody, with already kind of a clue of where this thing is going, that we're beginning this interval right here at a value of 1. If we go a little further with that same idea, move some things around here, all right, there's our first rectangle, we did that. The term at the very end of all this, which was right here, the 1 over 1 plus n over n, that is going to be the height of our last rectangle, or our nth rectangle. And in that case right here, the n over n, regardless of the value of n, is always going to become 1, and we end up with a 1 over 2 for the height of our last rectangle, which implies strongly then that b is equal to 2. So we kind of think that we can rule out option A, which was an integral from 0 to 1, and it's looking more like B or C or D. Now, in a way that I shouldn't show you guys in terms of cheating right here, we in the department have done some work on this. If you notice here that A and B are identical, except for one feature right here, and then B is identical to C and D in terms of its limits, but with different integrands, that really suggests that the one in the middle right here that has something in common with A, but something else different, and then something in common with C and D, but something else different, is probably the right answer. I probably shouldn't think too much about that, but let's keep that in mind. So it looks like right now we're at an integral then from 1 to 2. And now, guys, if we look at these values right over here, these are the y values we get at the beginning and the end of this. And it looks like what they have in common is simply a 1 over whatever your x value is. So that tells us that the function in question, the integrand, is most likely 1 over x. And if we put all that together, knowing that a is 1, that b is 2, and that our function f of x is 1 over x, we can say then with some confidence right here that what we're doing in this limit is really the integral from 1 to 2 of 1 over x taken with respect to x. And so the correct answer here is B. And this is just completely for fun here, but if you wanted to think about it, this is kind of what the thing looks like graphically. And what we're really doing here is a right Riemann sum, where the width of each one of those rectangles is going to be 1 over n, the same 1 over n we were given out in front of the original expression, and the height of each one of those rectangles is going to come by taking 1 over, and you would start with 1 and then add to that a 1 over n that you're going to get at each one of those spots right over there. And eventually, you'll end up with a 2 at the end for your x value and a 1 over 2 for your y value. Okay, so that's number 39.